Welcome to this video on sampling distribution of a difference between two means. By the end of this video, you should be able to calculate the mean and standard deviation of a sampling distribution of a difference between sample means, and, if appropriate, use normal distribution to calculate probabilities involving the difference between two means. All right, so today's scenario is we have ACT scores again, and now we have two different high schools, and we're wondering, there'll be a question at the end, who does better? And we'll find that out. So let's look at them independently. So we have Audrey Kell High School, and we have Providence High School. And so we are going to, with Audrey Kell, they have a ACT score that is normally distributed with a mean of 26 and a standard deviation of 3. And Providence High School has ACT scores that are skewed to the right with a mean of 25 and a standard deviation of 5. So think, skewed to the right means you have a bunch on the high end and only a few on the lower end, so they do pretty well. All right, now we will randomly select 25 students from AKHS, so I'm going to put N equals 25 here, and 30 students from PHS, N equals 30 here, just to help me kind of think about what I've got. So we're going to use the information given to describe the sampling distribution of the average ACT scores in the two samples. So this is when we're talking about one sample. We did that with our proportions too. Down here we'll talk about the difference between them. Okay, so looking for we're talking about one distribution at a time. So our Audrey Kell sample, the shape is going to be approximately normal. Because when you read this, it says the scores at this school are normally distributed. So we're going to say because the population is normally distributed. Okay, now let's look at the shape for Providence High School. It says Providence High School is skewed to the right, but here we're talking about the sampling distributions, not the population. Well, it's skewed to the right, but if we look at their sample size is 30. And remember when we talked about the central limit theorem, that if you had a sample size of greater than 30, your distribution would be approximately normal. And yes, there are different things that come in there, but 30 is going to be the number we're looking for. So we can say the same thing here, that it is approximately normal because their sample size is 30, which is greater than or equal to 30. So we have the central limit theorem enacted. Okay, so this is all my evidence of proving. I can't just put a check mark. I need to say why things are what they are. Now, define the means. So to find this first mean, remember the sampling distribution mean is going to be the same as the population. So Audrey Kell High School has a mean of 26. That means its sampling distribution will also have a mean of 26. And then when we look at Providence High School, it has a mean of 25, and so the sampling distribution will have the same mean. All right, now our standard deviation. The standard deviation for Audrey Kell is they have a standard deviation of 3 for the population, divide by the square root of the sample size of 25, and I got an answer of 0.6. Same thing for Providence. To find the standard deviation of the sampling distribution for Providence, they had a standard deviation of 5 divided by the square root of their sample size, which was 30, and I got their standard deviation to be 0.91. All right. So this is if we just looked at them independently. Now we want to find the difference in them. So we got to start putting some stuff together. And they're telling us to take Ardrey-Kell minus Providence. Okay? So to find the mean of Ardrey-Kell minus Providence equals 26 minus 25, which is 1. So the mean of their difference, it's an average difference of 1. Okay? Our standard deviation. So remember, when we're combining, we cannot add standard deviations, but we can add their variances and then take the square root. So our standard deviation is 0.6, so we got to put it in there, 0.6, and square it in order to be able to use it, plus the 0.91 and square it, which gave me a standard deviation of 1.09. Now, what is the shape of their differences? Well, if we look up here, we said both of these are approximately normal. So we got to bring that information down to here. Okay? And because both of those are approximately normal, that means our sampling distribution of their differences is also approximately normal. Because both sampling distributions are approximately normal. Okay, so let's take a look. We want to calculate the probability that a random sample of 25 AKHS students had a higher mean SAT score than a random sample of 30 PHS students. So what it's saying is, because we're going to do Kell minus Providence, if Kell is higher, their difference will be greater than 0. So we're really looking for what is the probability that Kell minus Providence is going to be greater than 0, is what we're looking for here. Okay, so let's draw our normal distribution, and we can do that because we've proven that this is approximately normal. So their mean difference is 1. And we have a normal distribution with a mean of 1 and a standard deviation of 1.09. And we want to know the probability that when I subtract them, I'm going to get an answer greater than 0. So 0 would be over here somewhere. And then I want greater than. So the area that I'm looking for is right here. So let's do our z-score. So our z-score, our score of interest is greater than 0, but that's our delineation mark. So 0 minus 1 divided by your standard deviation gave me a z-score of negative 0.92, and that makes sense. It's almost 1 standard deviation below the mean, and we drew it to the left. So when I look that area up on table A, I got 0.1788. Remember, table A gives you to the left, and we're asking to the right. So we just have to do 1 minus, and that gave us an area of 0.8212. So there's just over an 82% chance that you can get a sample that has Kell students outscoring Providence students. Okay? So let's look at the formulas that go with all of this. We've already done this very similar idea with proportions, and so it's the same idea. If we want to find the mean of the difference of two means, you just take their parameter mean minus the other parameter mean. Okay? because remember we're using an unbiased estimator, and therefore the sampling distribution will be the same as the population. Now this formula, what we did for standard deviation is we took the standard deviation divided by the square root of the sample size, but when we put it in we had to square it. Okay, and then same thing here. So these are ones, this is for the second one. And we had to square it, and that's really what we did right here. So what happens is when you distribute the 2 exponent through, you end up with a final formula of standard deviation squared, which is your variance, over your sample size, plus the variance for the second one. Variance is standard deviation squared over its sample size. So this is how we found these numbers. But when you look at it, when you're looking at the formula, this is what's going to happen to it right here. All right. So another thing I want to make sure when you're doing this, you must check both. Okay, and then the last thing, I keep showing you about the normal calculations where each of the numbers came from. It always looks the same here when we're plugging everything in. That 0 came from this right here, but we're saying x bar 1 minus x bar 2. That's where that number came from. Minus the 1 came from when we took our parameters and subtracted them. And the standard deviation is the variance divided by the sample size plus the variance divided by the sample size. Okay, so let's summarize this down so you have the really important information in one spot. All right, the first thing I want to summarize for you is the sampling distribution of the difference of the 2 means. To find the shape, really we need things to be approximately normal. So you need to check both samples, both distributions. Okay. And you have 2 choices here. It's going to be approximately normal if the population distribution is normal. Or, now this is an or situation, it's one or the other here. Okay, these are your 2 choices of what you want to use as your evidence. Or your sample size is greater than or equal to 30, so CLT is in effect. So that's for our shape. For our center, to find the mean of the 2, the difference of the 2 means, you're just going to take the population mean and subtract them. And your variability, to find the standard deviation of the difference of 2 means, you're going to take the variance squared from sample 1 and divide by its sample size, plus standard deviation squared or variance of sample 2 divided by its sample size. All right, now our normal calculations. I keep repeating them because I want to make sure we get this right and get it just as a normal part of what we've got going on in our brains. Okay, so we have our normal curve. The mean comes from subtracting the population means. The score of interest, whatever it is the statistic minus the statistic mean, and you'll want to shade. Don't forget to write that it is normal, and it's normal the difference of the two means from the sampling distributions and the standard deviation. Okay. And then our z-score, the numbers come from the first number as you take the two sample means, 1 minus x bar 2, minus the population means, the difference in the population means, divided by your standard deviation, okay, and then use table A. All right, what I'd like you to do is do the check your understanding and upload it into the assignment and the modules. And looking forward to seeing you in class. Let me know if you have any questions.